Hello and welcome once again. Today we'll be discussing on functional limits and continuity, which is a concluded portion of the first video on differential calculus. So I'm continuing with differential calculus as I said. So today what we'll be doing, we'll be finding limits of various functions. So what we mean by limits of a function, limit of a function. So basically, see, if there is a function like this one, so say like a function, we have a function here and fx equals to x square minus 9 over x minus 3. So now if we now just see what is the functional value, that is what is the value of f3. So we are interested to find the value of f3. So just see here, if we put x equals to 3 in this function, we will get 0 in the denominator, which will make the functional value undefined. So what we do in that case, so we see the limiting value of the function at x equals 3. So what we do, now we check the limiting value, limit x tends to 3, as the denotation says, fx equals to nice, is going good. So limit x tends to 3. We break the above thing in this form, that is a minus b into a plus b. And since x is approaching 3, so x is not actually equal to 3. When we say x is approaching a, it actually implies x is not equal to a. So x is in a nearby neighborhood of a. So x belongs to that small neighborhood of a. So next, so since x isn't actually equal to 3, we can cancel this. And what we get here is simply x plus 3. And if we put value, now x is approaching 3, we get 6. So what we have seen here, if we try to find the limiting value of fx at x equals 3, we get a value 6. So the limiting value of a function, let us go towards the continuity of a function. So now we want to explore what is the continuity of a function. What we mean by a continuous function at a point or at an interval or at a point. So now we have continuity of a function at a given point, say A. Now we are trying to understand continuity of a function by graphical method. So let us try to understand this graphically. So suppose this is the y-axis and this is the x-axis, and we have a point A here. So and it's a small neighborhood of A, that is a minus delta and a plus delta. And suppose we have a graph of fx, so say like this. So this is fx. Now what we mean by continuity of fx at point A, so when x is approaching A, that is x tends to A, then if fx tends to fa, we say f is continuous at A. So as this interval gets smaller and smaller, suppose so here is fa. If fa is here, then the functional value should be approaching fa. So it must be getting closer and closer to fa. That is the graphical concept of fx tending to fa. Now what we really mathematically mean or to say logically, by fx approaching f or fx is continuous at a. So we say fx is continuous at a point a if for all epsilon greater than 0 there exists and delta, which is the function of epsilon, which is also positive, a delta positive, such that fx minus some fixed L less than epsilon whenever x minus a less than delta. So if this holds whenever x minus a mod of x minus a less than delta, then we can say fx is continuous at a point a, and by definition fx is going to be equal to fa, and that is when we say fx is continuous at the point a. But this is not necessary. Fx can be continuous at the whole interval around a and not continuous at point a. F is continuous at a point a. Now if I say this mathematically, how to understand that if is actually continuous at a or not, then we check this. So what we check, if the limit extends to a minus. So what we mean by a minus, that is the interval a minus delta and a. So if in this interval limit extends to a, is fx is equal to fa, which must be equal to limit extends to a in the interval a plus delta fx, which is equal to fa, then we can say that f is continuous at point a. And for to be f continuous in an interval, that's a whole different story. Let's just restrict ourselves to the continuity at a point. Now let us do a problem. Let us move to a problem to understand better. Suppose, so it's a question. The question says f is from real to real. You must know this notation, all these notations, since you have learned function already. So f is from R to R. F is strictly increasing. So we know the meaning of f is strictly increasing, that is f of x1 greater than f of x2 whenever x of x1 greater than x2. So, and what more is given is limit x tends to infinite f of 3x by f of 3x by f of x is equals 1. Then what we need to find is limit of x tends to infinite f of 2x by f of x. We need to find this, and the options are given as 2 over 3 upon 2, C is 3 and B is 1. So grab your pen and copy and give it a try. So do alongside with me, and if you have found the answer, that's great. I hope you have given it a try, and now I'm going to solve it. Okay, so since fx is strictly increasing, can we say that f of 2x is less than f of 3x? Can we say that? Okay, f is not strictly, f is increasing actually, so it may be less than equal. Okay, so we can say that, right? And then moving on. Okay, now dividing by fx all the three sides. and fx is always positive. Remember that fx must be positive in this case. Otherwise we can't divide. Yes, that isn't mentioned, so that should be mentioned in the question. And so now we can apply, this is equals 1. So now we can apply the sandwich theorem. So the sandwich theorem, you already know this. If you don't, please check out the previous video. So limit by sandwich theorem, limit x tends to infinite 1 less than equal limit x tends to infinite f of 2x over f of x less than equal limit x tends to infinite f of 3x by f of x. Now we know this value 1. Here it is given. So by sandwich theorem we can say the value of this is also equals 1. So we are done, and our right option is D. Now in case of sandwich theorems, you always have to remember one thing. I always warn you about not overdoing it or not over exploiting the theorem. Sometimes you may always find yourself in false positions. Like I'm saying, suppose say there is a function like this one. Say what? So suppose there may be a function fx, and that is maybe like, so sometimes you might be tempted to attend the sandwich theorem on gx itself. So if you may apply sandwich theorem on gx separately, and maybe also apply sandwich theorem on hx separately. So that won't work. That is totally wrong. Sometimes you may get the right answer, but that isn't the way. If you have to apply sandwich, you have to apply on whole of it. That is, you have to apply sandwich on fx itself. That is right, but this thing is totally wrong. So remember it. Now we are going to see a nice function and some concept related to it. That is, if we say of a function like so you may be already familiar with this function, that is fx equals sine of 1 by x. Now I want to check continuity of fx at x equals 0. Now I want to check this. So how would we try it? So you can see that we can't put x equals 0 and then it becomes sine of something infinite equal, and then that has no value, that has no sense. Actually putting x equals to 0 has no sense in itself. So we have to find the limiting value. So we are rather interested in limit of x tends to 0 if x equals to sine limit of x tends to 0 sine of 1 by x. Now what is interesting is that there is a discontinuity. You will know, you might know that sometimes we have this limit x tends to, suppose a minus fx equals to limit x tends to a plus fx. These both are equal, but either fa, maybe fa is not equal to this, so fa might not be this order. So sometimes that is removable discontinuity to remove. So it is called removable discontinuity because we can remove that discontinuity and make it continuous by making fa equals to both of these two. So that is not the case here, but let's just see. So what we can do here is we can write, suppose say, okay, so let's say x equals, first we take x equals 1 over n pi. Okay, so we take x equals to 1 over n pi. So when we say limit x tends to 0, naturally this implies n tends to infinite. Okay, now we put this information in this fx. So if I write limit x tends to 0 sine of 1 by x is similar to, so I am using a dummy variable, so that is nothing different, so you can always do that. And we know by the general solution of trigonometric equations and solution of trigonometry, we can know that this value is always going to be 0. So sine of n pi is always 0. We don't have to check if n is going infinite or anything else. So it is always 0. And then we can also check. Okay, so this part is done. We can say now take x equals 2 over 4n plus 1 pi. So you might be intrigued by what I am trying to do. You might be intuitively knowing what I am trying to do here. So you can always guess what I am trying to do. So this time also, if limit x tends to 0, you can see that limit n tends to 0, n tends to infinite in this case. So by in that similar way, we can write limit x tends to 0 sine of 1 over x equals limit n tends to infinite sine of, so that inverts that this, since it's 1 by x, so 1 by x is, so 1 over x we get 4n plus 1 by 2. So this becomes this thing, 4n plus 1 by 2. So now by general solution, we know this, what the value of this sign? Yes, we know that, and that is 1. So we got two different limits on the same limiting value, that is x is approaching 0, but we get a different value. So we get two different values in x approaching 0, and hence the limit doesn't exist. So sometimes the limit might not be existing, and that is a discontinuity obviously. Sometimes maybe both these parts exist, like this might exist, and also this might exist, but these are not equal. In that case, it is also a discontinuity, and sometimes f a is also undefined. So in that case also we have a discontinuity. Now suppose fx is x over x into sine of 1 over x for x not equals 0 and 0 when x equals 0. So we can partly define a function to make it continuous at a point. So if we haven't defined this, if we haven't made 0 in x equals 0, so this fx would not have been continuous. So how do we prove that fx is continuous here? Okay, so now we are going to the epsilon delta definition. By that definition, we can say for all epsilon greater than 0, there exists delta positive such that what is fx here? Fx is x sine 1 by x minus f of 0, that is 0, less than epsilon, whenever x minus 0, that is mod of x, is less than delta. So you can always give me a delta, I can make x, so you can always give me a x and I can always find a delta such that mod of x is less than delta, and then we can fix that x here, and this thing gonna be less than epsilon. So x into sine of 1 by x is always continuous in this case, where f of 0 is 0. If you change f0, what will happen? If we change f0, then it will be not continuous at 0. Okay, now here is another question, which I think it came in some AIEEE or JEE. That is 1000 minus 1 power n x power n. So give it a try. This is not so tough, but you need to know tree and use the tree wisely so that we can get to the answer. So hope you have given it a try, and now I'm going to solve it. Okay, so what we've got here, this is simply minus x plus x squared minus x cubed plus x to the power 4 and so on, goes up to power 1000, that is x power 1000. So if we calculate that GP, this is a geometric progression of common ratio minus x, this will end up like this one. Sorry. This is plus. So now what do we do? Is there any way you can think of? Okay, there are many possible ways you can do this, but what I'm going to do is I'm going to using L'Hopital's rule. And what L'Hopital's rule tells is that there are some necessary conditions you should always keep in your mind for L'Hopital's rule to hold. Condition to hold. So what are those? So first one is limit of x tends to say some a may be finite or infinite, if x equals to equal to 0 or plus or minus of infinite. Second is limit so g dash x should not vanish, that is g dash x should not be, that is differential that is derivative of gx should not be 0 at the interval of a. And third is this limit should exist. If any of these rules get violated, don't think of applying L'Hopital's rule, or you will get a wrong answer. So similar to the sandwich theorem, L'Hopital's rule should be used very wisely to get to the right answer. So think over it and then apply. So in this case we have got both infinite by infinite, so both are in indeterminate form, and what we see is g dash x, that is 1, so it doesn't vanish over any interval, and moreover this limit also exists, so we can apply here. There is no problem in that. If we know, if you are wise about the rule, we can always apply. So differentiating that numerator gives, and the denominator gives 1. So this limit is basically infinite. So this function or this limit converges to infinite. So that is different from not non-existence of infinite, non-existence of limit. This limit exists, but the limit is not finite. The limit is infinite. So please try to understand this. You have to always know this limit exists, but the limit is infinite. Now I'm going to say some things. Now what I am trying to make you understand about L'Hopital's is, suppose say there is a function like this one, limit x tends to infinite, 1 plus sine of x by x. Now apply L'Hopital's rule here. So what do we get? Differentiating, that is cos x over 1. now we know that limit x tends to infinite. Also we just saw that okay, so we always know that cos x, so cos x has no proper value, that is limit x tends to infinite, cos x doesn't exist actually. So this doesn't exist. Since we know cos x is an oscillating function, cos x is an oscillating function, so it always oscillates. So there isn't any finite value to this thing, or even an infinite value. So this limit doesn't exist, we can actually say, because cos x is an oscillating function. But is that true? But when we think of this function, is that true in that case? Does it really hold? What do you think? No, it actually, this is wrong. So this is the violation of root 1. So in this case, this is indeterminate, the denominator is indeterminate, but we can't say about, we are not true about the sin x portion. So sin of x when limit tends to x tends to infinite is not infinite. So we can't say. So both are in indeterminate form. So this is a root, this is false. So if we just clever enough, so what we can see is 1 plus sin x by x can be written as the same thing, is written as sin x by x. Now we can apply this rule, right? We learned that limit of x tends to a fx plus gx is same as limit x tends to a fx plus limit x tends to a gx. We learned that. No, we know this is very simple formula, and fxgs must be continuous. So in this case 1 by x is continuous, we all know, and sin x by x is also continuous. So we can apply here. So limit x tends to infinite, 1 by x is 0. Cool. And what about this? We can apply sandwich easily. So sin x is always minus, and then we can apply divide by x on all sides. So when we have give limit x tends to infinite, in all this case we get 0. This is limit x tends to infinite sin of x by x 0. So this has a value 0 by sandwich theorem. So what we have got here, the value is 0. But we applying L'Hopital's rule, we got the limit doesn't exist. So that isn't true. So be very careful when we apply L'Hopital's rule. Okay, so here is the problem. If x equals to tan of pi over pi into box of x minus pi by 2, and that divided by 2 plus box of x squared. So you know what is box x, 4x, or greatest integer function of x I have written here, you can understand. Now we aren't going to solve this problem, we are just going to solve this problem in our mind. So this is very easy. If you understand this is very easy. So I would tell focus on the box part and then give it a try, and when you're ready come back. So I think you have given it a hopeful try and a wholehearted try. So what we can write here is solution is what is, see that this part is always an integer, this box part is going to be an integer always. So that is the function of a greatest integer function. We know that greatest integer function always gives us an integer. So this would be tan of k pi for any, that is k belong to integer, and for any value of x this would be always tan over k pi, and we know that tan of k pi is equals to 0 for any k belonging to the integers. So and this part is always going to be positive, and this is always going to give us a positive number, so there is no chance of getting this term 0, getting the denominator 0, and Hence we get fx equals to 0 for all x belonging to R, and that gives our answer. So what should be our answer? Our answer should be continuous at s, continuous for all x belonging to R. And check all the leftover options, and yes, no one is working, so only the option A is correct. So here is another problem. We have p equals to limit of x tends to 0 plus. I already told you what we mean by x tends to 0 plus, and then 1 plus tan square of root x over power of 1 by 2x. Then what will be the value of log p? So give it a try, and now I am doing the solution. So what is log p? Log p will be 1 over 2x, the power comes down, and log of 1 plus tan square root x. Okay, moving on to the next step, we get log of 1 plus tan square root x by tan square root x into tan square of root x by 2x. So what I am trying to do with this is I am trying to apply the formula, the basic limit formula we all know. Limit x tends to 0, log of 1 plus x is by x is equal to 1. So check that this is x is dummy here, nothing more. So we can replace it by u, interchange with u, and then change. We are not going to do all that because that would take time, and we don't have much time in Wbjee or even in JEE. So we check that this is similar to some u tending to 0. Okay, that would work, and then so this is going to 0 1. So this is 1, and we have left is tan square root x. So write it in this way, tan root x by, and we have a half root x. So I am writing in this form. As we all know that limit x tends to 0, tan of x over x is equals to 1. We all know that. This is a very basic limit formula as the first one. So you can check always all the math textbooks, and if you want, then we can prove for some later videos. You can always do that. There is no problem in that, and we get the value half. So it is b. Okay, so here is another problem that says that we are going to find the value of this limit, this function, and we have to find this limit. So I'm going to the solution. You can see the board what is the question. Give it a try. I don't have to tell all the time. Give it a try and then come back to the video. So what we can do here is, so these are all tricks. I'm just tricking. So that we can get the above thing in some regular form, which will be useful to us. Now I'm taking this portion and writing, just reversing it. So what we get, that is, if this is fx, so we are writing 1 by fx minus 1. So we get a 4x, and since we do this, we also have so what makes this famous, what makes this simple is that it is written in the form 1 plus fx minus 1 over 1 of or fx minus 1. So see this portion, this is similar to this, and we know this is e, we all know that limit x tends to infinite, and this is e when fx is equal to 1. So we can write here this and move the limit over here. So what we simply get, limit x tends to infinity in x squared plus x plus 3. So we know this denominator, this is going to be nothing but this is 0. So we get e power 0, which is 1. So right option is A. So here is another problem. This is I think it came in some AI. This states, as the question states, fx is continuous in a whole interval of 0 to close 0 to and x0 equals to f2. Then the equation fx equals to fx plus 1 has. So we are going to find the number of solutions of the equation fx equals to fx plus 1 in reference to these options. So this is not. So okay, we are not going to the option right now. We are going to directly to the solution. So let us just know how we are understanding these videos, and always feel free to comment and always feel free to do constructive criticism. We always appreciate that. So feel free to let us know how the video is to you, and how we are getting to know things, and how is your preparation after watching these videos. So that would be very nice to us. So I am going to tell a very important property of here. So just check. So you can take some function gx equals to fx minus f of x plus 1, and that won't change much of thing. So gx is a function which is equal to f of x minus f of x plus 1. Now what we do here is we check g of 0. G of 0 is f0 minus f of 1, and g of 2 is f of 1 minus f of 2, and what we know is f of 0 is to f of 2, so f2 minus f1. Now clearly g0 and g2 have opposite signs. Why? Because gx is continuous, f is continuous, so the difference of a continuous function is always going to be continuous. So this function is continuous, and since g0 and g2 have opposite signs, there must be at least a root, at least one root. Sorry, I made a mistake here. This is not g2, this is g1. One real root in 0 1. So that should be true, and we check this is true, and also this is true. So both the options are B and C are true. So this property is known as intermediate. So this property of functions is known as intermediate value property, where a function, if a function is continuous and have two different signs over a point and over an interval, then we can say that the function has at least one root or maybe two roots according to the question. So that is the intermediate value property. So like if I want to elaborate, I can say if a function is like this, suppose it is 0, it is 1, so suppose this function is going like this and then this. So you can say that there is a, so this is continuous and it's changing sign, so it is here positive and then negative. So if we get this value and get this value and see that they both are opposite signs, we can say that this has a root in 0 1. So that is the matter. That is the point. So here is another problem, the final problem to today's session. The integer n for which the limit x tends to 0 cos squared of x minus cos x. So something that is a that I am not going to repeat is finite non-zero integer. So this is our point of focus. So this is our point of focus is finite non-zero integer. I could have given you options, but that won't help either. We can always this problem doesn't require an option. You can consider it as an integer variable, integer type question. So anyways, moving to the solution. What we have is, if we just rearrange the numerator part, we get, check this by your own, verify this. If I have written right or wrong, verify it by yourself. So this, we get the simplified part, and now what we are going to do is another concept. So I wrote this problem, that's the reason why I wrote this problem. So this is the series expansion of cos x. As many of you might know, or some of you might not know, that isn't a great deal. That isn't a not a much worry. You will always end up knowing these things. So no need to worry. We are here for you. So this is the series expansion for cos x. You not need to know much. And the series for e power x series. So what is basically, these are power series, all are power series. There is a definite way to get all these formulas, but we are not going to show this now. And so on. And this is minus x cube by 2 all over x power 9. Okay. So hope you have understood up to this. Next, what we're gonna check is this. Okay, so there was a 1. So this 1 and 1 cancels out, and over here also 1 and 1 cancels out. So if we add those, and then what we get, simplified thing. I'm writing the final thing to do it by yourself. By 2, and then that is x power 5 by 12 and x power 5 by 24, and so on. We are not much interested in the next part, so we can save our time in this way. So always try to make your time work, and so these next terms are not required because we are finding a finite non-zero integer. So up to this is enough, we can understand very easily. So what should be the value of n? So clearly, if you want a finite non-zero integer, we should have the value of n should be equals to 4. Why? Because if it is 3, then this part would be 0 and this would be also 0. So this would be n equals 4. So the answer is n equals 4. So this was so I conclude today's session, and hope you have understood some of it. And till then, see you again. Tata.